All right, how is everybody this morning?
Good.
Good? Okay, cool. Right on. Okay. So today we're going to start with a review of series parallel circuits. We talked about series parallel last time. We said they're really a combination of series circuits and parallel circuits, just like the name sounds. So we're going to do a brief example on the board of a real world instance where you might use series parallel circuits. And then I want to just go over one of the takeaways from the lab that we did last time. And then we're going to go on to our main topic for today, which is Kirchhoff's laws. So there are two laws that Kirchhoff came up with. And really what they are is really just formal ways of saying a couple things that we've already seen. Okay? So when I was going to school and I heard about a law named after a person, I always got a little bit nervous because I figured that if something was named after a person, it must have been really complicated. Otherwise, nobody would bother to, name that after the discoverer. It'd just be another fact. But it turns out that Kirchhoff's laws are really not that complicated. They're really just formal ways of saying things that we have already talked about in class. Okay? So that's really what they are. So you might ask, why do we need these formal ways of writing this information down if we've already talked about it and we already kind of have an understanding? Well, when we're working on circuits with 2 or 3 or 4 resistors, we can kind of go through and do them all by hand and do the calculations that way and sort of look at it and kind of look at it like a puzzle and go through and figure out what to do next. But when you start looking at circuits that have 10 or 100 or 1,000 different components in them, then you really need a much more systematic way of going through and analyzing what's going on in those circuits. It becomes too large to just sort of puzzle it out. So if you're going to have a systematic and formal way of going through those, you need formal definitions of this information. And that's really what Kirchhoff's laws are. So they help us if we're trying to analyze larger circuits. And you might say, well, larger circuits are analyzed by computers. Well, guess what? What do you think the computers are using? They're using Kirchhoff's laws under the hood. Okay? So these are formal ways of writing down information that we know, and they help us when we're analyzing larger circuits. So then after all that hand waving, we get on to the actual laws, and I'll tell you what they are. And then after all of that about Kirchhoff's laws, we're going to go on to a slightly different topic, which is voltage dividers. So really a voltage divider is anytime you have 2 or more resistors in series. And they're called voltage dividers because they take the full voltage and they divide it up among the resistors, okay? So we'll talk about voltage dividers at the end there. And then we'll go on and do a preview of today's lab. So that's the plan for today. Any questions before we get going? Okay, cool. So then let's go and talk a little bit about series parallel, like we discussed last time. So rather than just kind of summarizing this, I want to give you a real-world example. So imagine that you finish up your school and you get hired and you're working at your first job and it's your first day. You come in and your boss says, it's great to have you. We're so glad we hired somebody who knows about electronics because we want to design a new circuit, okay? And we want you to help. So with this new circuit, we have this product, and it's going to have 5 lights on it, okay? These little lights are essentially like little resistors. So each one has a resistance of 200 ohms. We have a voltage source for this project, which is 10 volts. And we want each light to have 20 milliamps flowing through it. Okay? So your boss tells you all this. He says, this is our specification. Go out and design us a circuit that will meet these specifications. Okay? So this is, something that you might actually see if you went out and started working in the real world. So let's kind of work through this and see how we might come up with a design that meets these specifications. Okay? So we have a couple of different options here on how we could design this, right? We know about series circuits, we know about parallel circuits, and we know about series parallel circuits. So let's start with the simplest. Let's start with a series circuit and see how that would work. Maybe that'll work out for us, and then we can just be done. So let's think about how that would work. So we know we have a 10-volt power supply. So we got 10 volts here, and then we've got these little light bulbs that are 200 ohms each. And we know that we have 5 of them. So maybe we can just put them all in series. So let's see how that would work. So we got 1 there, and then there's 2, 3, 4, and 5. So that would be a series circuit with 5 of these little light bulbs all in a row. So they're 200 ohms each. So let's see how that would work out. Let's see. So far, we're doing pretty well. We've got 5 lights. They're 200 ohms each. We've got 10 volts on our power supply. So the last thing we need to check is whether we're getting 20 milliamps per light. Okay? So let's figure that out. So how could we analyze this circuit? What could we do to figure out how much current we're getting for these light bulbs? What would be the first step here? Yeah, probably the total resistance. So remember, we can do Ohm's law eventually, but that only works when we have just a single resistor. So we want to take this circuit that has 5 resistors and find the single equivalent resistance so that we can use Ohm's law. So we want to redraw the circuit. We know we still have a 10-volt power supply here. But we want to redraw this as one single equivalent resistance. So how do we find the equivalent resistance for a set of resistors in series? Yeah, we add them together, exactly. So we've got 5 lights that are acting like resistors. Each one is 200 ohms. So what's the total resistance there? 1,000, exactly. So this is like a circuit with an equivalent resistance of 1,000 ohms. So any questions about that? All right. So then now we have a circuit where we have a single voltage, a single resistance. So now we can use Ohm's law to figure out the current. So remember, Ohm's law is like this. We've got V, I, and R. So we want to figure out the current. We write down I equals, and then we cover that up. We see that it's V over R. So then, in this case, the voltage is 10 volts, and the resistance is 1,000 ohms. So 10 over 1,000 gives me 0.01 amps. We know that the unit is amps. It comes out in raw units because we put the values in raw units, volts and ohms, okay? So we get 0.01 amps out. So how many milliamps would that be? 10. Okay, so does that meet our specification? No. So, okay, so that design doesn't quite work. It would have been nice because it's just nice and easy, but doesn't quite work, okay? So so series didn't work. So we also know about parallel, okay? We know about how we could make a parallel circuit. So let's see how that would work. So we've got, let's try that. We got a 10-volt power supply here, and then we could put these light bulbs in parallel. So we could have a light bulb there, and that would be 200 ohms. And then, yeah, we could do that 4 more times. Okay, so, yeah.
So is it saying that you need 20 milliamps total, or it just needs to be on the...
No, 20 milliamps each per light. Yeah. Yeah, other questions? Okay, so now, again, we've got our 10-volt power supply. We've got 5 lights. They're 200 ohms each. So now we need to check the current through each light. So what could we do to check the current through the lights here?
Power?
We'll get to power in a little while. We're not there right now.
We have the voltage and we have the resistor.
Yeah, exactly. Yeah. So in this case, right, we got the voltage from the power supply here, and since this is a parallel circuit, yeah, that voltage is the same for all the components. So yeah, we have that voltage and we have the resistance. So we can use Ohm's law again. So we could say, again, we're trying to find the current. We say I equals V over R, and in this case, V is 10 volts, and R is 200 ohms here. So then, what does that come out to be? 10 over 200.
50 milliamps?
Okay, yeah, so that would be 0.05 amps or 50 milliamps. So we're still not quite there. Before we were too low on the current, now we've got too much. So we want that Goldilocks zone right in the middle, okay? So unfortunately, this parallel circuit isn't going to quite work either. So series doesn't work by itself. Parallel doesn't work by itself. Can anybody see a way that we might be able to modify this circuit in order to reduce that current a little bit and get us the 20 milliamps that we want?
We make some of this in series.
Yeah, we could. So let's say, right, a couple of good ideas there. So we could put 2 of them in series, say. So then you would have 10 volts. So for this, we could look at this branch, okay? So then you'd have 10 volts across. You could use Ohm's law again. You'd say I equals the voltage, which is 10 volts. And since these two are in series, you would find their equivalent resistance by adding them together. So that would be 10 volts over 400 ohms. So that comes out to be 0.025 amps or 25 milliamps. So that's really close, but it's still not quite what we're looking for. Okay, so It was a good idea, but that's not quite going to do it. So, so is there something else that we could do to reduce the current in each of these branches? Well, remember on our first day of class, we had that circuit with the LED, and we said that we couldn't have too much current flowing through that LED because it would heat up and get damaged. So what did we do to reduce the current through the LED?
Add another resistor.
That's right, we added a resistor. So maybe we could do that in this case. So we could put a resistor down here. Okay? But now, how big should that resistor be? Kind of a tricky question.
What, don't they all have to be 200?
No, the light bulbs are 200 milliamps, or I'm sorry, 200 ohms each. But if we are adding our own resistors, we could pick any resistor value we want. Okay?
You can use Ohm's law.
Ah, we could use Ohm's law. Yeah, that's a good idea. So now we know that we want to have 20 milliamps flowing through that branch of that circuit. So we know what current we want, and we know the voltage from one side of that circuit to the other. So then we could use Ohm's law to figure out the total resistance that we need for that branch. Okay, so let's do that. So in this case, we're trying to figure out the resistance. So we write down R equals, and then we cover that up. We see that it's V over I. So then, in this case, our total voltage is the 10 volts. And then the total current is 20 milliamps. Should I just write down 20 on the bottom there? No. Yeah, so I need to convert that to raw units. So that would be, instead of writing 20 milliamps, I would write 10 volts over 0.02 amps. Okay? So what do I get if I do that division? Does somebody have a calculator?
500.
500. Okay. So 500 ohms. So we know that the total resistance for this branch of the circuit here has to be 500 ohms. And we know that this light bulb is supplying 200 ohms. So how much resistance should this other independent resistor have? 300, exactly. So that's how we get 20 milliamps flowing through that branch. And then we could do the same thing for the other branches so that we have 20 milliamps flowing through each light. So that's an example of how we can design a series parallel circuit in order to meet certain specifications. Okay? So that's kind of a real-world example of how you might go about designing a circuit like that. So any questions about that? Okay, cool. All right. So then, so that was an example of a series parallel circuit. So then let's go on and talk a little bit about the lab last time. And I wanted to point out one thing about the lab that was a little bit subtle that might not have been immediately clear. Okay? All right, so in the lab last time, you made a circuit on a breadboard and it looked something like this. We had a power supply here that was 12 volts, and then we had a circuit with a resistor up there, and then one down there, and then one across the bottom, and then also another resistor over there. Okay, and the lab asked you to measure the voltages across these resistors. So we had something like 4 volts up here and 6 volts down there, and then 2 volts across that resistor, and then 2 volts across that resistor. Okay? And then the lab asked you for the total voltage on this circuit. So when it asks you for that, the total sounds like, you know, you add up a bunch of parts. So it's tempting to look at this circuit and say, okay, the total voltage is just the sum of all of those individual voltages. But let's look at what happens when we do that. So if we add these all together, we get 4 plus 6, well, that's 10 volts, plus 2 is 12, plus 2 more, that would be 14 volts. But we're only supplying 12. So we can't have a total voltage that's more than we're supplying, okay? So something weird is going on here. So how is it possible that if we add up all of the individual voltages, we get more voltage than we're supplying? Are we creating free energy here? Did we just discover cold fusion? I mean, we could be making a lot of money here. But maybe not, maybe not. So what's going on is you can think of these voltages kind of like building blocks, okay? And the total voltage is like the total height of this tower that you're building, okay? So when you have resistors in series, that's kind of like stacking building blocks on top of each other, okay? So what you have down here at the bottom is you have a 6 volt drop across that resistor. So that's like having a building block that's like 6 inches tall, okay? And then up at the top, you have a resistor that is 4 volts across it. So that's like having a resistor or a building block that's 4 inches tall. But then right here in the middle, you've got these 2 resistors, and they have 2 volts across each one, but they're parallel. So when you have resistors in parallel, that's almost like having blocks that are side by side. Okay? So that's kind of like having blocks in your tower that are stacked side by side. So these blocks in the middle are 2 inches tall each, but they're side by side. Okay? So if somebody were to ask you to calculate the height of this tower, you wouldn't just add up 6 plus 2 plus 2 plus 4, because these 2 blocks in the middle are side by side, okay? So if somebody asked you to find the total height of this tower, you'd add this one, and then only one of these heights, and then that one, okay? So the same thing is going on over here with our circuit. When we're asked to find the total voltage, we add up this 6 volt, and then only one of these 2 voltages here, because they're in parallel, okay? So 6 volt plus 2 is 8, plus 4 gives us the 12 volts, okay? So that's why the sum of our voltages comes out to be greater than the total voltage, because we have these 2 resistors in parallel, okay? So are there questions about that? And that's kind of related to Kirchhoff's laws. That's related to Kirchhoff's voltage law. And we'll talk about that today in just a minute, okay? But this is sort of an informal way of understanding what's going on in this circuit. And Kirchhoff's voltage law is a formal way of saying that, okay? So, yeah. Any questions before we go on? All right. Cool. So then let's go on and talk a little bit about Kirchhoff's laws. All right. So, like I said, Kirchhoff's laws, there are two of Kirchhoff's laws. There's Kirchhoff's voltage law, and Kirchhoff's current law. And these are almost always abbreviated because nobody can remember how to spell Kirchhoff. It's got two H's and two F's and it's just weird, okay? So these are abbreviated KVL and KCL, okay? It's much quicker and easier to say and easier to spell. So these are Kirchhoff's laws, and I'll tell you exactly what they say in a minute. But really, what they are is formal ways of saying things that we've already talked about and already have a basic understanding of. Okay, so they're formal ways of writing those things down. So we need them because when we start to analyze larger circuits, we need a formalized process. And so we need very clear definitions of exactly what we know. And these laws help us with that. So let's go on and talk about the laws themselves. And let's start with Kirchhoff's current law. So Kirchhoff's current law says that the sum of all currents into any node equals the sum of all currents out of that node. Okay, so that sounds kind of weird, but let's break it down. So first of all, you might wonder, what is a node? So a node is just any point on a circuit. So this is saying that if you look at any point on the circuit, you look at all the current that's flowing in, it has to be the same as the current that's flowing out. Well, we've seen this before, right? Remember, we've looked at a circuit and say we got 3 wires coming together like this. And they come together at an intersection, and we know that we have, say, 10 milliamps flowing there, and then we've got 7 milliamps flowing out down that way. How much do we have flowing that way? 3. We just used Kirchhoff's current law. There you go. So this junction is the node that we're looking at. This intersection right there is the node. And we look at all the sum of all the currents flowing in, that's 10. It has to be the same as the sum of the currents flowing out. So if we have 10 milliamps flowing in, we got to have a total of 10 milliamps flowing out. Okay? So we've talked about that before, right? We've all seen that. Hopefully we have a little bit of familiarity with that. So Kirchhoff's current law is just a formal way of saying that. Another way to think about it is that current does not build up at any point in the circuit. So if current flows into a point, it flows right on out. It doesn't like pool anywhere in your circuit, okay? So that's what Kirchhoff's current law says. That's all it is. So any questions about that? Okay. All right. So one down. So now let's talk about Kirchhoff's voltage law. Anybody want me to go over that or do another example or anything?
Yeah.
Yeah? All right. All right. Let's do another example. So we said that a node can be any point on a circuit. So let's say we've got a wire here, and we've got some other branches of the circuit going off that way. But we're going to pick a node that's right here, right in the middle of this wire. Okay. And now let's say we have 13 milliamps flowing into that node. How much is going to be flowing out of that node? 13, exactly. So we could pick a node right in the middle of a wire. Kirchhoff's current law says this works for any node. Normally, we pick a node, at an intersection of several wires because that's more interesting, but we could pick one right in the middle also. Okay? Or we could do one more example here. Let's say we've got a four-way intersection, and we've got, say, we know we have 15 milliamps flowing down that way, and we've got 5 milliamps flowing up that way, and we've got 8 milliamps flowing that way. And we want to figure out how much current is flowing in this wire over here, okay? So first of all, is this current going to be flowing into the node or away from the node? Yeah, it is. It's going to be flowing into the node. We know that because we have 20 milliamps flowing out between the top and the bottom here. And so we better have 20 milliamps flowing in. And so far, we only have 8 milliamps flowing in from that side. So this one has to be flowing in as well. And then how much current will be in this wire? Yeah, 12, exactly. So that would be 12 milliamps there. So again, it's just saying that the total currents flowing in has to be equal to the total current flowing out. So if we have 20 milliamps flowing out, we better have 20 milliamps flowing in overall. Okay?
15 minus 8.
What's that?
So the current flowing out is positive and the one flowing is negative. So 15 minus 8 plus 5.
Yeah, so 15, yeah, minus, so you could call the current flowing in positive or, yeah.
On that calculator.
Yeah. Mm-hmm.
Hey, Professor, can you do one example a little more higher?
Oh, I'm sorry, it's a little low. Yeah, sorry about that. Yeah. So, Yeah, so let's say we've got a three-way junction here, and we have 12 milliamps flowing that way, and then 4 milliamps flowing that way. So how much current would be flowing in this branch here? So yeah, if we wanted to do it and write it out formally, we would say that the sum of the currents flowing in equals the sum of the currents flowing out. So the sum of the currents flowing in would be 12 milliamps plus 8 milliamps. I'm sorry, plus plus 4 milliamps has to equal the amount of current. No.
Wouldn't it have to go out?
Yeah, you're right. It would have to go out. Thank you. Yeah. So 12 milliamps plus 4 milliamps flowing in equals the amount of current that's flowing out. So in this case, 16, exactly. So we would have 16 milliamps flowing out here. Okay. So yeah, any other questions? Okay. All right, so then let's go on and talk about Kirchhoff's voltage law. Okay, so Kirchhoff's voltage law says the sum of all voltages around any loop in a circuit equals 0. Okay? And a loop is any path that starts and ends in the same place. Okay? So let's look at that circuit that we drew on the board earlier. So we've got 12 volts here, and then a resistor, and a resistor, and then one more resistor over here on the right. Okay, so and we said that the voltages here, we had 4 volts, 6 volts, 2 volts, and 2 volts. Okay? Now, the one extra wrinkle with Kirchhoff's voltage law is you have to know which side of the voltage is positive and which side is negative. So the power supply will be labeled. One side will be positive and one side will be negative. And then with the resistors, generally the side that's closer to the positive terminal will have the positive, a higher voltage. And the side that's closer to the negative terminal will have the lower voltage. Okay, so your voltages would be like that. So Kirchhoff's voltage law says if you add up all of the voltages around any loop in the circuit, they all add up to 0. Okay? So let's see what that is talking about here. So let's draw a loop first. So we could start our loop down here at this point, and then we could make the loop go around the circuit like this and come back to where we started. Okay? So then we can add up all of those voltages and see if they really do add up to 0. So we're starting here, and now we're going across a 12-volt difference here, and we're going from lower to higher. So this is like going uphill. So we would add that voltage. So we would say plus 12 volts, and then we're going across a 4-volt difference, and we're going from positive to negative. So we're going downhill here. So 12 volts, so we would subtract that. So minus 4 volts, and then we go down another 2 volts, so minus 2 volts, and then minus 6 volts. Altogether, that equals, Kirchhoff's voltage law says that needs to equal 0. So if we check this out, sure enough, we have 12 volts minus 4 is 8, minus 2 is 6, and minus 6 is 0. So Kirchhoff's voltage law works there, okay? But that's not super useful because we already knew what all of those voltages were. So that was just sort of checking out that it worked. But say we didn't know what this voltage was over here on the right side, okay? What we could do is we could do that same thing, but we could make our loop go around this outer part of the circuit. So we could start our loop here and then go up this way and have the loop go all the way to this outer branch and then come back here. Okay? And so then we could add up all of those voltages. And we could call this one our unknown voltage. We could call that the question mark voltage for right now. Okay? So then we could do Kirchhoff's voltage law with that. We would, again, start right here. So we're going up by 12 volts. So 12 volts positive, and then minus 4 volts. And then minus our unknown voltage, and then minus 6 volts, altogether equals 0. Kirchhoff's voltage law tells us that that has to equal 0. So then we could figure this out to find our unknown voltage. So 12 minus 4 gives us 8, and then minus 6 gives us 2. So 2 volts minus our unknown voltage equals 0. So that tells us that our unknown voltage is 2 volts.
Is what again?
So you were wondering about how we got that last step?
Yeah.
Yeah. Okay, so we look at this line here. We could kind of change the order around a little bit if we wanted. We could say this is 12 volts minus 4 volts, and then we could just kind of swap the order of those last two if we wanted. So we could say minus 6 volts minus our unknown voltage equals 0. And if we add and subtract all of these things together, this gives us, so 12 minus 4 is 8, minus 6, that's 2 volts. Yeah, and then minus our unknown voltage equals 0. So our unknown voltage has to be 2 volts. Okay? So that way we could use Kirchhoff's voltage law to to find this unknown voltage. And there's even a simpler way to do it. Because we said that this Kirchhoff's voltage law applies around any loop in our circuit. Okay? So rather than having all this other stuff in our loop, we could have just picked a loop that went from here around this part of the circuit and then ended up back there. Okay? That's a loop. It's a path that starts and ends in the same place. So that would be a loop also. And we could do Kirchhoff's voltage law around that loop. So if we did that, we would say that, so we're just starting there. We go up by 2 volts, so plus 2 volts. And then we go down by our unknown, so minus our unknown voltage equals 0. So we can see right away then that our unknown voltage has to be 2 volts. Okay? So you can pick any path that you want around the circuit as long as it starts and ends in the same place. Then if you add up all the voltages around that path, they have to add up to a total of 0. Okay? So that's what Kirchhoff's voltage law says. And again, this is kind of saying something that we already knew. Remember when we talked about this circuit at the beginning of class, we said that if you wanted to find the total voltage here, you would only add up, you would add the top voltage and the bottom, and then only one of these 2 voltages over here. We said it was kind of like adding, stacking building blocks on top of each other, and it is. But this is another way to think about it. This is saying that you only add up one of those because you're going around a loop in your circuit. And that loop only goes through one or the other. Okay? So that's another way of thinking about it. And again, this is, we have seen this before today as well. We've said that, if we have 12 volts here, then, and we have a circuit like this, then the voltages across these resistors have to add up to our supplied voltage. And so, yeah, Kirchhoff's voltage law is really a formal way of saying that, okay? So again, it's not as necessary when we have smaller circuits, but it becomes much more important when we're looking at larger circuits that are more complicated, okay? So any questions about Kirchhoff's voltage law? Okay. So those are the 2 laws. Kirchhoff's current law says that the currents coming into a node have to be equal to the currents flowing out. And then Kirchhoff's voltage law says the voltages around any loop have to add up to 0. Okay? So then let's go on and talk about something different, which is voltage dividers. So a voltage divider is really just 2 or more resistors in series. So you might wonder, well, why would we give a fancy name to such a simple circuit, 2 or more resistors in series? We've been looking at that for a long time. Well, what happens is that when you think about it as a voltage divider, it can be very useful. Okay, so let's look at an example here. So say we have a power supply that's giving us 10 volts. And then we have 2 resistors in series. So this is a voltage divider. And they're each 1 kilo ohm. Okay. So if we do our basic analysis, we know that this is a circuit that is equivalent to 2 kilo ohms. So then we could do Ohm's law, and we would say that I equals V over R. So that's 10 volts over 2,000 ohms. And so then that comes out to be 0.05 amps, or I'm sorry, 0.005 amps, or 5 milliamps. Okay? So we have 5 milliamps flowing through here. So we have 5 milliamps flowing through there. So then we can figure out the voltage across each of these resistors. We would say V equals IR. So that's 0.005 amps times 1,000 ohms. So that gives us 5 volts. And the same thing happens down here, 5 volts. So now maybe it's a little bit clearer why we call this a voltage divider. We started off with 10 volts and we divided it into 5 volts and 5 volts. Okay? So this is a voltage divider because it takes your total voltage and it divides it among your resistors. Okay? And hopefully it seems clear that if you have 2 of the same resistors here, each one will get half of the total voltage. Okay? And if you have more than 2 resistors, and they're all the same, say you had 3 resistors, they're all the same, each one would get 1/3 of the total voltage. Okay? So say you have a 12-volt supply, and you've got, say, 10 kilo ohms on each of the resistors. Then you've got 3 resistors in series. Each one is the same resistance. So each one is a 1/3 of the total resistance. So each one gets 1/3 of the total voltage. So this one would have 1/3 of 12 volts. So that would be 4 volts. And then 4 volts. And 4 volts down there. Okay? So we take the total voltage and we divide it between the resistors. Okay? So that's why we call this a voltage divider. It takes the total voltage and divides it among the resistors. So why would we care about this? Well, oftentimes we have a circuit and we've got a big power supply and we need to have a voltage in that circuit at some point that's less than the total supplied voltage. Okay? Sometimes we need to have half of the total supplied voltage. And if that's the case, we can just use a voltage divider with 2 even resistors and then split the voltage in half that way. Okay? This is useful in a lot of sensors. They have something called a bias, which is an initial voltage that's half of the total voltage. That way, the output voltage starts off at that halfway point, and it can go up or down depending on the signal that the sensor gets. So it starts off right in the middle of the total voltage so that it's got it's got enough room to go up and down, depending on what signal it's getting. Okay, so that's a common use for a voltage divider, and we're going to see that later in the semester when we look at our fiber optic communicator kits. So with those kits, we have a microphone, and that microphone creates an output voltage, and that output voltage goes up or down depending on the sound pressure that's hitting the microphone. And so we want that output voltage to start right in the middle of our possible range so that it has equal distance to go up and down. And so we use a voltage divider for that. Okay? So that's a common use for voltage dividers. That's why we care about them. Sometimes you have a voltage divider where the resistors are not all the same value. And in that case, we need to use a formula to figure out the voltage across a particular resistor. So that formula is V. So VR equals. So let's say we'll call that VR1 equals V total times R1 over R total. Okay? And that formula works for these types of voltage dividers as well. So we could figure it out for this one, say, or let's do it for this one. So VR1, let's figure out the voltage for the top resistor. So it would be V total, which would be 12 volts here, and then times R1 over R total. So that would be 10 kilo ohms over 30 kilo ohms. So that would be 12 volts times 1/3, or 0.333, and that equals 4 volts. Okay? So that formula works for any set of resistors. If all the resistors are the same, we can kind of take this shortcut where we just divide the total voltage by the number of resistors. But if you have varying resistor values, then you can use this formula to find the voltage across any resistor. Okay? So questions about that? Okay. All right. So then, if there's no questions about that, we'll go on and do our preview for today's lab. So today's lab starts on page 103 in the lab book. And the first part is in multisim, and we have a voltage divider with 3 resistors in series. We've got 12 volts over here. So what voltage do we expect across each of these resistors? Yeah, 4 volts, right? We're taking 12 volts and we're dividing it into 3 parts. So each one should be 1/3 of that total. So 4 volts, okay? But we can use multisim to confirm that. So you'll run the simulation and you'll look at the voltages on each of these meters, and then you'll write down those voltages down here, okay? And then you'll switch the resistor values around and you will repeat those measurements, okay? And you'll change the battery voltage as well. So any questions about that part? Okay. And then you'll go on and you'll fill out this table, and you can see here that now in this one, not all resistor values are the same, okay? So, so in this case, you're not going to have the same voltage across each resistor. You'll have slightly different voltages. So you'll fill out that table there. Then you'll go on and you will look at this circuit, and you can see this is a voltage divider with 5 resistors in series. So you will figure out the voltages across each one of those resistors. Okay? Again, you just run the simulation and look at the voltages on the meter, although hopefully after our lecture you would be able to figure those out as well. So, questions about that? All right.
Woo!
All right, it's a good day. All right, and then over here, we have, we need to change the wording in the lab book a little bit. There's a typo here, okay? So in part G, it says construct the circuit in, and then it doesn't say in what, okay? So it should say construct the circuit in part 1A using the following components on a breadboard, okay? So you're going to build a circuit on a breadboard, and the one that you're going to build is the one from the beginning of the lab. It's this one in part 1A with the 3 resistors in series, okay? So you're going to build this on a breadboard using the resistors shown in this table, okay? And then you're going to measure the voltages across those resistors using a digital multimeter. So this is a physical circuit that you're building, and you're making real measurements, and you're writing down your values there, and then recording the total voltage. And then you're going to recreate that in multisim. You're going to do the same simulation in multisim, and then you're going to compare these. So do you think that the values you get from multisim are going to be exactly the same as the ones from your circuit board?
No.
No, exactly, because there's tolerances in the real world and things aren't perfect. But hopefully the 2 tables will be pretty close to each other, okay? All right. And then down here, you're going to be opening up this circuit in multisim and making those measurements, the currents for the whole circuit and the current for path A and path B. And then you're going to go on and do the same thing. You're going to measure the current for this circuit and this circuit down there. So, yeah, so that's what we're working on today in the lab. So, any questions about that? All right, then I will take attendance and then I'll let you go.